Hey there everyone, welcome back. In this example, it's another one on the conservation of energy. However, we're going to utilize both conservative and non-conservative forces. All right. So in this problem, as you can see, we have a box that's starting with some initial speed denoted by the arrow, and it's at an initial height of h1, right, at point A. And we want to find the speeds at a couple points, right? Down here at point B, up here at point C, which is at a height of h2, and then after C, it slides along a section of this horizontal track of length L and some coefficient of friction, right? And then we want to find first if it has enough energy to make it through that entire stretch. If it does, what's its speed at D? And if it doesn't, how far along that stretch will it stop? Okay. So we have a couple numbers up here, a couple variables. But just looking at this problem qualitatively, for part A, and finding the speed down here at B, right? It starts with some initial kinetic energy, right? It says it's moving with a speed of 6.4 meters per second. So initially, what types of energy does it have? Well, it has energy of motion, right? So kinetic and potential energy. I say and potential because I'm going to set the zero height down here, right? I'm going to measure potential energy from down here, in other words, because I think that's easiest, at least in this problem, because I've specified, or rather this picture specifies the height of h1 from that point already, right? But you can just as easily say, oh, potential energy is zero at this height, right? The height of C. That's up to you, right? You can even put zero up here. You just have, a negative change in height. That's another thing about potential energy is that it's arbitrary. You can measure it from wherever you want to. Okay, so you have that freedom to choose whichever position is simplest to measure from that you want. Okay, so in part A, we want to find the speed at B. So initially, it has kinetic energy, and I'm going to say it has potential energy, right? And because this stretch here is a frictionless stretch, right? All that, right? There's no energy lost, and so it's a conservative conservation problem. Thus, energy initial equals energy final. There we go. Now let's just plug in the expressions. So initially, 1/2 mv initial squared plus plus mg, and they call that initial height a height of h1. And then lastly, at point B, that's our quote-unquote final position. It's going to be actually increasing speed, right? It will have gotten faster down here. Why? Well, the energy that was potential up here is being converted into kinetic energy down here, right? As it's falling, it's speeding up and speeding up. Thus, more and more potential energy is being converted. But again, if you add up the sum at both points, it's equal to zero. Right? Or rather, sorry. The change from initial to final is equal to zero. The total energy at A is whatever it is, some number, I don't know. But that's equal to the total number at B. Those are the same numbers. Okay? All right. So K final is 1/2 mv final squared plus, since I'm measuring from the height of B, I'm just going to say that's plus 0, right? The height at B is 0, so that term is 0. And what are we finding? Well, we're finding the final speed. We're finding VF, okay? So after a little bit of algebra, you can actually cancel out mass if you want, right? 1, 2, 3. There you go. And so we're simply multiplying this whole thing by 2. multiplying the left side by 2, rather. Oops. Canceled out mass, but then I put it back in. Plus GH1. And then we're taking the square root, right? So if you plug in all of those numbers, it should be positive. Let's hope it is. I get a positive 12.1 meters per second. Okay, that's the speed at point B. And yes, indeed, it is larger in magnitude than what it started with at point A, which was 6.4, right? So it almost doubled in speed. All right, so for part B, we'll move on to the next slide here. We want to find the speed at C. Okay, so speed at C. We can actually do this one of two ways, right? It's still a frictionless problem, right? So it's still a conservative energy conservation problem. We can do the delta U from one of two places. We can do this change in height, right? Or we can just do from part A down to C, right? And say we go start at A, end at C, or we can start at B and end at C, whichever you want. So I'm going to do it both ways. If we start at A and end at C, we have the following. We have the speed at point A, right? Because it has some kinetic energy. It also has some potential energy at A. And then at point C, well, it will have some speed. How do we know it has speed at C? Right? Pause the video and try and reason to yourself why it has speed at C. Okay? So the reason it has some amounts of speed, or in other words, some amount of kinetic energy at C, is because this change in height, h2, is not equal to h1. In other words, the energy here is converted into a kinetic, and then it is not reconverted all the way back into that same amount of potential energy, right? So there is some extra kinetic energy, right? Not all of this potential has been reconverted, just a little bit, right? If, for example, this track wasn't here, and then B went all the way up like this, right? And then C was up here. If this was the case, this block, well, how high would it go? Well, it would go to the initial potential energy height plus some height that was the initial kinetic. Okay, so that could be another problem to solve. But for right now, let's solve what the problem says. So let's see, whoops. All right, so at C, we have some leftover kinetic energy, which I'll call, let's do final, that's fine, plus mgh2, and nothing cancels out here, right? Again, I'm measuring from down there, right? So nothing cancels out. And what we're trying to solve for is this final speed, okay? So actually now you can also cancel out mass. And then after a little rearranging, we get, let's see here, 1/2 v initial squared plus gh1 minus gh2, and all of that times 2, and square root of all that. We should get a speed of, where was it? About 9.8 meters per second. And so if we compare this value to the answer we got in part A, right, it's a little less, right? The speed at C is a little less than the speed at B. Why? Well, it's decreased its kinetic energy a little bit by the amount of mgh2. So it's taken away a little bit of kinetic energy, right? So it's moving slower. And you can do from B to C, right? So now the initial point is down here at point B. Well, let's see, we have initial kinetic energy. I'll do that. And plus 0 for the potential energy, because it's where we're measuring it from. And the right side should stay about the same. Okay. And so again, after some algebra, whoops, we don't want squared. Masses cancel. After a little bit of algebra, we have 1/2 v initial squared. And again, this is the speed at B, right, which we found in part A, minus GH2. That's all times 2 and square rooted. And this should give you the exact same value as above, right? Because it's the same speed, right? The problem, the situation isn't changing. We're just calculating it from a different point, right? We're using two different initial points. And lastly, in part C, does the block reach point D? Okay, well, let's see here. What do we need to answer? Oops, let me go back. We need to answer the question of, does the block at point C have enough energy, both from kinetic and potential sources, to overcome the energy lost due to friction in order to move the entire length L? Ask it another way. Does the force of friction acting on the block in this case expel all of its initial energy, right? Or is some left over? To answer that, we can, let's see, part C, we can use the non-conservative energy conservation equation, right? Work non-conservative equals delta K minus delta U, okay? Or, right, plus a negative delta U, right? And so this is the same as that non-conservative force, which is friction, times the distance, in this case L. So let's see. What's the change in kinetic energy? Well, to be honest, we don't really know that, do we? We don't really know that. We know the change in U. That's not changing height. So that's 0. Okay? So this is 1/2 mv initial, v final squared minus 1/2 v initial squared. And that's equal to the force of kinetic friction times L. What's Fk? Well, let me draw a tiny free body diagram over here, right? When the block is on that frictional path, right, there's a force of kinetic friction, that direction. But there's also the normal force, and that's counteracted by the gravitational force, mg. So this equals, let's see, a negative, let me back up a little bit. Let me put it up here. This is a negative mu k times the normal force, then times L, right? This here is the kinetic frictional force. And by the way, I should have a negative here. That negative is because the force is in the opposite direction of the displacement. Okay? Remember, it's still work done. Work still follows integral f dot dr. Okay? So, in this case, we have negative mu k, and then the normal force is simply the object's weight, mgl. Okay? And what we want to solve for here is the final speed, right? The final speed. You could also, I suppose, put a final speed of 0 and see what L is, but I suspect that won't work very nicely for you, right? We want to solve for the final speed, okay? Before we do that, we want to see if the total energy before is equal to the total energy after, right? Or not equal to, but greater than or less than. So let's see here. All right. Let me get situated. Okay. So we want to see, again, if the kinetic energy before it hits the track is greater than or less than the work done by friction, right? If it is, the box will slide through the entire length L and have some final speed. If it's less than the work done by friction, then the box stops and we can solve for distance. So we want to actually put in the initial speed here. So this is 1/2, the masses cancel, right? And the initial speed, what's the initial speed? Well, in this particular case, it's the initial speed at point C. That's the speed that it starts to strike the frictional surface with. So what's the speed at C? Well, we found that in part B. So that's 9.8 squared, and that's equal to negative the coefficient, 0.72 times 9.81, and then the length of that frictional stretch is 12 meters. Okay, sorry. This shouldn't be equal. It should be, is it greater than or less than? Okay. I'm not worrying about the final kinetic energy yet because that's not needed, because we really want to know if the initial kinetic energy is greater than or less than the work done by friction. Okay. And so in this case, it turns out to be, let's see, 48.02. And then the work done by friction is a whopping 84.76. Okay, I'm not going to put units because they're a little messed up, right? But the numbers are such that the work done by friction is greater than the object's initial kinetic energy at point C. And so it won't make it across the frictional surface. Oh no. So now we want to solve for at what distance along L does it stop. Okay, and this was part D, I believe. Okay, and so now we do know the final speed. The final speed's 0. So we can say the work non-conservative is equal to the delta K. And this is the work kinetic energy theorem from last chapter. So the force is the kinetic force, the distance is L, and it's a negative because, again, they're in opposite directions. And here, it's 1/2 mv final squared minus 1/2 v initial squared. Okay? Almost done. The final speed, we know what that is 0. So, rewriting this again, I guess the negatives cancel, don't they? We have the coefficient K times mgl equals 1/2 mass initial speed squared. Masses cancel again, right? And we're solving for, whoops, sorry, not L, but D, right? The distance, right? The distance. because the energy drops to 0 after this block has slid a distance d, and that's not the same as capital L. Let's see. So we're solving for d in this case. So that's initial speed squared divided by 2 times mu k g. Plug in those values. We should get a distance of 6.8 meters. Okay, and it turns out that that's just past halfway along that track. Okay, so that's the speed at which the object comes to rest finally, right? The energy has been completely dissipated by the frictional force, and that frictional energy cannot be put back into the block, and that's why it's a non-conservative work, right? That's why we use this non-conservative energy equation right there. So turns out that the block comes just past halfway, right? And then comes to a stop. All right, thanks for watching.